You know, machine learning is pretty much everywhere you look these days. It's behind your movie recommendations, it's what's filtering out junk from your inbox, and it even helps you beat the traffic. A lot of the time it feels like, well, like magic, right? But it's not. It's actually a super fascinating field of science, and it's all built on a handful of core ideas. So let's dive in and pull back the curtain on how machines actually learn.
So it really all boils down to this one simple but kind of profound question. I mean, what does it actually mean for a machine to learn something? When we say a computer has learned, what does it actually know? What does that knowledge even look like inside the machine? To really wrap our heads around this, we're not going to start with a bunch of boring, abstract theory. Nope. We're going to start with something way more concrete. Just plain old data.
Okay, so check this out. I want you to imagine you're a machine for a second. This is what you're given to work with, a simple table of houses. On the left, you've got the size of the house in square feet, and on the right, you've got the price it sold for. Your job, as the machine, is to figure out the relationship between these two columns. Why? So that you can predict the price of a brand new house that you've never, ever seen before. And believe it or not, this simple idea is the heart of our first major type of machine learning.
And that brings us to our first category, supervised learning. I like to think of this as the taskmaster approach. It's kind of like a student cramming for a test with a huge stack of flashcards. On one side of the card, you have the question, like the square footage of a house, and on the other, you have the answer, the price it sold for. The algorithm's whole job is to go through thousands or even millions of these question and answer pairs and figure out the general rule that connects them.
Right. So the secret ingredient here, the absolutely crucial thing, is the labeled data. You can think of it as the answer key for the test. The machine isn't just taking wild guesses in the dark. No, it's being supervised by the correct answers, hence the name. The whole point of this is to build a little rule, a model, that can take a new question it's never seen and get the output right, just like that student who can now ace the test.
Now, under this big umbrella of supervised learning, there are really two main jobs the machine can have. The first one is called regression. That's exactly what we were just talking about with the house prices. You're trying to predict a continuous value, a number that can be anything along a scale. The other main job is called classification. And here, you're not predicting a number. Instead, you're trying to pick a category. The classic example is this email spam or not spam? It's a yes or no, this or that kind of problem.
So let's zoom back in on that housing price problem. With regression, the goal is actually pretty simple to picture. The algorithm looks at all those dots on a graph, each one representing a house, and its mission is to draw the one single straight line that best cuts through all of them, the one that best captures the trend.
And boom, here it is. This is what that learned rule actually looks like. It's a line. Each of those little dots is a real house from our data. And that line, that is the model. That's the knowledge the machine has learned from all those examples. So now, if you come along with a new house, say 2,000 square feet, you just find that spot on the bottom axis, go straight up to the line, and hang a left to see the predicted price. It's so simple, but it's incredibly powerful.
Okay, so what about classification? Well, the goal here is a little bit different. Instead of drawing a line through the data to find a trend, the algorithm learns how to draw a line between different groups. Just picture it. You've got a cloud of dots over here that are all spam emails, and another cloud over there that are legitimate emails. The model, the thing the machine learns, is the boundary line that does the best job of separating those two groups.
All right, so supervised learning is great if you have an answer key. But what happens when you don't? What if you just have a giant pile of data with no labels? Well, that brings us to our next category, unsupervised learning. And the best analogy for this one is a detective. You show up at a crime scene, you've got all these clues, the data, but nobody's there to tell you what any of it means. It's your job to find the hidden patterns all on your own.
Yeah, the key phrase here is unlabeled data. There are no right answers to learn from. The algorithm just gets this massive jumble of information and is basically told, here, make sense of this. So it's not about prediction, it's about discovery. It's about finding the hidden structure that's already there in the data. Think about things like automatically grouping similar customers together for marketing, or spotting a really weird transaction that might be fraud.
A perfect, everyday example of this is clustering. I mean, think about your phone's photo app. How does it automatically create those little folders with all the pictures of the same person? Nobody told it who was who. It just looked at all the photos and figured it out on its own by finding groups of faces that look similar. That's clustering. And a really classic algorithm that does this is called k-means. Let's actually walk through how it works, step by step.
Okay, so this is where it all begins. This is what the algorithm sees, just a big cloud of data points. Notice there are no colors, no labels, no groups, nothing. It's just raw, unstructured information.
To our eyes, we can kind of see two distinct blobs, right? But how on earth can a machine figure that out on its own? Well, it all starts with a completely random guess. The algorithm literally just drops two cluster centers, those little crosses you see, somewhere in the middle of the data. And yeah, they're almost certainly in the wrong spot to start with, but that's okay. This is just step 0. Now we get into this little two-step dance that the algorithm does over and over. Step 1, the algorithm looks at every single data point, one by one, and assigns it to whichever of those two centers is closer. It basically paints each dot the color of its nearest center. As you can see, we've got two groups now, but they look pretty messy and not quite right. And here's step 2 of the dance. The algorithm looks at all the red dots, figures out their average location, the center of that red cloud, and moves the red cross right to that spot. Then it does the exact same thing for the blue dots. See how the crosses just jumped to be more in the middle of their own color groups? That's the key move. And then it just does it again. That's the whole magic trick. It goes back to step 1, reassign every point to its new closest center. Then step 2, move the centers to the new average location. Assign, update, assign, update. It keeps doing this little dance until the groups stabilize and the centers stop moving. And just like that, without any help, the algorithm has found the hidden structure in the data. The answer just emerged. Pretty cool, right? All right, on to our third and final major category, reinforcement learning. So if supervised learning is the student with flashcards, and unsupervised is the detective finding clues, then reinforcement learning, well, it's the game player. It's an algorithm that learns how to win simply by playing the game over and over and over again, through pure trial and error. So here's how it works. You have an algorithm, which we call an agent, and you drop it into some kind of environment, like a video game. The agent can take actions, move left, move right, jump. After each action, the environment gives it some feedback. It might get a positive reward, like plus 10 points for grabbing a coin, or it might get a penalty, like minus 50 for crashing into a wall. The agent's entire goal is to figure out a strategy that gets it the most points possible over the long run. So you really just have these 4 key parts, right? You've got the agent, that's our learner, our player. You've got the environment, that's the game world itself. You've got the actions, those are the possible moves. And you've got the reward, that's the score. By playing the game literally millions or even billions of times, the agent just learns through experience which actions in which situations lead to the biggest rewards.
Okay, so we've got these 3 fundamental pillars of machine learning: supervised, unsupervised, and reinforcement. But that all leads to a really big question, right? How do we get from these basic ideas to the massive, mind-blowing AI models we see today? The ones that can write poetry or generate computer code or create stunning art. How do these foundational concepts scale up to do that?
Yeah, let's just ask the question directly. How in the world do you go from drawing a simple line through house price data to building something as complex as ChatGPT? The answer, it turns out, is a really clever twist on supervised learning, a trick that lets us tap into an almost unimaginable amount of data. And that breakthrough is called self-supervised learning, and it's an incredibly clever idea. Imagine you take a sentence from a book, like "The quick brown fox jumps over the lazy dog." Now you hide one of the words, so the machine sees "The quick brown fox jumps over the lazy blank," and its task is to predict the missing word, dog. You see what just happened? The data itself created the flashcard. The sentence with the blank is the question, and the original word you hid is the answer. You can do this automatically for billions of sentences.
And this is the absolute game changer. This self-supervising trick means you don't need an army of humans to sit there and label data for you anymore. You can just unleash your algorithm on a colossal, unlabeled dataset, like, I don't know, pretty much the entire internet. And by simply playing this fill-in-the-blank game trillions of times, the model starts to learn incredibly deep patterns. Not just grammar and vocabulary, but facts about the world, how to reason, context, and nuance. This, right here, is how today's giant foundation models are built.
So there you have it. From learning with an answer key, to being a detective that finds hidden clusters, to being a game player learning from rewards, and now to teaching itself using the entire internet, we've seen the core ways that machines learn. At the end of the day, it's all about one thing: finding patterns in data. And what's so wild is that now they're finding those patterns in the biggest, most complex data set imaginable, the sum of our collective human knowledge. Which really leaves us with one final, fascinating thought to chew on. If machines can now learn from the vast patterns of all our data, what will they eventually end up teaching us about ourselves?